So the next event this morning is a lecture by Bảo Châu Ngô, who has many accolades, but I'll mention just one. It's Fields Medal 2010, citation for his proof of the fundamental lemma in the theory of automorphic forms through the introduction of new algebra geometric methods. And the topic of the lecture is Galois theory.
Right. One of the most satisfying aspects of mathematician work is this feeling that what we do can be traced back to the early history of human mind and hopefully may propagate to the futures as well. So this is particularly true for Évariste Galois and in the most of us, in much more modest extent. But let's talk about Galois. So Galois' invention of the Galois Group follow attempt to solve polynomial equation of low degree, which arose as early as mathematics exist. And the Galois Group itself continued to be the central object of study of contemporary number theory. So let me show this. I think I talked about this equation yesterday in high school in Heidelberg. So this is the, of course, this is solution for the quadratic equation that you all learned in schools. And, quite surprisingly, you can find some equivalent form of that in the Babylonian tablet that date 2,000 years BC. And it's much more difficult when you move to cubic equations. You can find a solution to a large numbers of cubic equations in Chinese and Persian forms dating around 10th centuries, but certainly not the German forms. The German form has been discovered in Italy in Renaissance by half amateur mathematician, half gamblers, named is Tartaglia, and this is his solutions. So let's try this reduced form, right? Eliminate one of the coefficients, it's easy to eliminate it, and then this is the solutions. It looks complicated, and then I think the very few of us is clever enough to fight by ourselves. I cannot fight by myself. It's elementary, but it has series of very clever and tricky change of variables. But I don't want to discuss only change of variable. I just discuss some aspect of it that that pertain to the Galois theory. That actually there's the formula itself has some problems, right? In the Italian times, all the numbers we know are real numbers. So here P and Q are real numbers, and we are looking for the real solution of cubic equation. So here, obviously, we have to assume that this discriminant, the p squared over 4 plus q squared over 4 plus p third over 27, we assume it to be positive, so you can take square root, right? That is all right. But then you have real numbers, you can take cubic roots. So that's okay, that is a Tartaglia solution. But well, this is quite problematic. What happened when the discriminant is negative, right? This is not giving the real solution. And when you have 3 real solutions, this only give one of them. What about the 2 others? So there is something not completely, not completely complete about Tartaglia solutions. And that exactly, try to dig deeper into that, into the birth of the Galois theory. So, for example, when you look at later we have the complex numbers. The complex number is much better. You have cubic equation have 3 solutions always, right? So these equations would give you solutions, but that is not quite right when you look at it, because of course there is a square root. That can be the plus or the minus compensating out, so you can ignore that. But then if you take the third root, complex have 3 third root, right? So you cannot take the 2 third root independently. We then have 9 solutions. We expect only 3 solutions. So this choice had to be related somehow, right? So there is something to say about Tartaglia solutions. And later, after Tartaglia and Cardano, another Italian Renaissance man, Ferrero, found an even more complicated solution for quartic equation that I will not speak about. I don't even know the formula. So it's kind of pointless to dig into that. But at this point, you can say about what you really mean by solving this equation. So what you're looking for is some kind of formula like this. And the solvers, what occurs in the formula should be the coefficient of the polynomials, right? And then you can use the 4 operation, plus, minus, multiplication, and division, and taking root, second root, third root, as much root as you can. But then, of course, here we have an ambiguity about taking roots, because there's 7 choices, which one we had to do. So attempt to solve quintic and higher degree equation have been fruitless until Abel and Ruffini showed it is impossible to find solutions to general polynomial equation degree 5 and more in these forms. So this is what the Abel-Ruffini theorem cannot find a formula with coefficient of polynomials with the 4 operation and taking couple of roots. It was spectacular as it was. It did not fully answer the questions because Abel-Ruffini theorem did not tell you if you give you one equation, it does not tell you if you can solve it by radicons or not, right? The general equation did not, but specific equation, it cannot say it. That was Galois who introduced, you can solve all this equation by say one shot, just by genius definitions. And then introduced this Galois group. And by a Galois group, of course, you can reprove Abel-Ruffini theorem, and which is kind of much more nicer for me is actually you can use calculation Galois group to recover all the tricky calculation of Tartaglia, Ferrero, and so on. Right? So this is not my intention to do the Galois theory class here in 45 minutes. But I want to stress that actually we can understand the essence of it just by analyzing very carefully the meaning of the original questions. All right, so first of all, you have all the coefficient A1, H2, AN of these polynomials. You then want to add them, minus, and subtract, multiply, and divisions. So that just means that you have somehow the structures, right, in which you can do those operations. So that is what you have the fields. The fields is algebraic structures in which you can do that operation. So to start with, you have to be given a field that I call the field K. So the field is algebraic structures, I think most know what it is, and in which you can do addition, subtraction, multiplication, and division by non-zero numbers. All right. And here I do something more, much more a radical thing that I have this K-bar, right? We know that if equation with rational coefficient may not have rational solutions. Equation with real coefficient may not have real solutions. So there's a way to add on these solutions in a consistent way to build a much larger field which can algebraic closures that could K-bar. So all the elements of K-bar are solutions to some equations, and all the equations have enough roots in K-bar. So assume that exists. That is non-trivial assertion, but assume that exists. All right, so now I'm given polynomials, P, xn, a1, xn minus 1, an, one with one variable, x, and its coefficient is given fin k, right? And it has on the roots, n roots, if you count them with multiplicity in k bar, the algebraic closures, right? And I think I think I go slightly too fast. Let us come back to the Tartaglia formula with this complicated formula. I think the one single question you have to ask before trying to find the solution is, actually there's something wrong about the question itself. So we want to find a formula for the solution of this equation. But there's not one solution, there's n solutions. So there cannot be a formula, right? The formula must have one single. So there's something wrong with the formulation of it, because there's some kind of ambiguities between the roots, and the Galois theory is actually what is kind of encoding that ambiguity between the choice of roots. So another more subtle example, see, when you look at very simple equation like x to the 7 to 1, right? 7 roots of 1. So there's root 1, and there's another root, located, distributed on the unit circles. So there's the first one on the primitive root of 7 primitive root of 1, and on the others are just power of that one, right? So if you know one, and you know somehow on the other just by making some powers. But that's not true for other equations. In the equation, if you know one, you may not know others. Others' roots cannot be expressed as the polynomial of the first one because you can move them around somehow. So that is the Galois group E. So the whole there is kind of dependence between roots can be encoded into the very single object that is it. We look at on the gamma k is Galois group of k bar over k, that all automorphism of k bar. So on the transformation preserving algebraic structures and preserving k. And because preserving k, preserve these equations. And as you know, just act on this set of roots. And that's about it. And the thing is that the way that it acts on roots depend on the polynomial you choose, right? So given the action, that the way you can encode it, look at the kind of homomorphism group from this kind of huge Galois group into the group of permutation with n element. So what we get is a subgroup of the group of permutation. So in the case of the x to the 7 to 1, the group is very small. It's just some kind of Billian group, 6 element. But then in the case of the general polynomials, the group is as large as symmetric group. So the complication, you can measure the complexity of the equation by the size of its Galois group. So I go in the Galois group of polynomials, the image of this large absolute Galois group in the group of permutations. So now it's a little bit technical, and not to be just technical, but you can the Sohn-Webern group, if you can have a series of normal subgroup, so that in each step the ratio is a Abelian group, right? And and Galois theory claims that you can solve the equation if and only if this gamma p is Sohn-Webern groups. So you can see that the group of permutation 3 variables is Sohn-Webern can easily exercise this permutation group of 3 variables. You can do it for 4 permutation, but you can show that the 5 permutation group is not Sohn-Webern. That is how you cannot solve the equation degree more than 5. And also, the very nice thing is that just using this kind of series of subgroup, you can there's very practical exercise to recover the solution of Tartaglia and Ferro and so on. It takes some time, but any student Galois theory can do that. All right, so I want to come back to this. So the whole point of Galois theory is this move from studying equations, algebraic polynomial and one variable, its solution, into something, it's just a completely different looking object that is some abstract group, gamma P, the Galois group, acting on finite set element. And all you want to know about the solution equation, it can be expressed in these very simple forms. Right? For example, the equation have a root in K itself, and if only if you have a fixed point. If you have one of the fixed point fixed under the Galois group. Right? And the polynomial is irreducible if the action is transitive. You can move one to another, and so on. So that is somehow basically the end of Galois theory, that we can have Galois group, and you can, whatever you want to know can be expressed in these forms. But there's some the large unknown things is the Galois group itself. Well, it define it in very abstract way. We certainly don't know what this group it is. Certainly enormous, and I don't know if I make an example. Yeah. So for complex numbers, Galois group is trivial because complex number is algebraically closed itself. For real numbers, it's Z mod 2Z. For finite fins, Z mod PZ is the hat. So the one thing you know about the Galois group is a pro-finite group. So it's a limit of finite group, so the pro-finite completion of the group of integers. And some even more complicated for the fin of Laurent formal series. But the big mystery is what is Galois group of Q. That is on what number theories want to know. And somehow smaller mystery is still very large is what is Galois group of periodic integers, periodic numbers, for example. So that is the kind of object that number theories want to understand. So now, before coming back to this, I want to make an excursion into something very seemingly unrelated, some topology. There's something notionally very important in basic topology called fundamental groups. So, let's look at start topology and refer to the torus, right? This looks like a donut, and this is some first non-trivial object in topology. And the first thing you have to understand is called the fundamental groups. So you start X is a whole torus, and the small x is some point on it. So here it's just the intersection of the red circle and the blue circle. Right? And you look on the way, you can travel on a route and come back to itself. That's called the loop. Right? And here, you have you can see that you have one loop, the blue loop, and the red loop. Right? And so the trivial loop that you don't move. And there's no way that you can deform continuously from the red loop to the blue loop. So that kind of two different elements of the fundamental group. So fundamental group is on the loops up to the homotopy equivalence. That means the way you can deform continuously one loop to another. And in this case, elliptic curve in topologically it's just R squared divided by Z squared. And the fundamental group is very simple, it's the Z2, Z squared. But in general, the fundamental group can be very complicated, non-commutative groups. So it doesn't seem to have much to do with Galois theory, but it does. The thing is called the next chapters in algebraic topology 101 class is called the covering theory. So covering is this kind of picture. So here is, I don't want to draw the donut anymore. I should draw some kind of circle, the kind of circle band, right? And the covering is something like something above, right? Covering is so that if you check every point in X in the lower space, and you check the pre-image of some kind of smaller neighborhood, pre-image of small disk, then it would be just n different disk, the same thing above. So because of that, if you allow the root on downstairs and you move on upstairs, you may not end up into the same point, but it end up to the point, another point in the same fibers, the mapping also to the same point X. And that's why the fundamental groups of X act on the fibers, right? Just by moving points over groups and to see how this thing move on the covers. that give you an action of the fundamental group on the fibers of the coverings. Right? So again, you have an action of pi1 on the covers. So this say that the covers is completely determined by that action. The covers is just given by this finite set, the fibers, the point of y mapped into x, and the action, the fundamental group on that set. Very much like Galois theory, right? And vice versa, you can somehow have a version of fundamental group defined by the covers. If you know on the covers, then there's some kind of group behind that. And this is almost a fundamental group. So they call the completed fundamental group because it's all know about the finite things. So the finite pro-completion, the fundamental group, something by one. But at this point, it becomes completely analogous from the Galois theory and the fundamental groups. That is the point of Grothendieck, who can define fundamental group to form more complicated object algebraic varieties, not by doing loops, but looking on the covers. Right? The category of covers provides something that looks like fundamental groups. So it becomes unifying fundamental group topology in one way and fundamental Galois group in number theory and fundamental group in topology. All right, and so if I start now coming back to a story about equation, right? You have first we try to solve one variables, right? Now what about solving system of 5 equations, 2 equations, 5 variables, right? It's much more complicated. And that is a system of equations with many variables called algebraic varieties, because algebraic variety is a system of equations, polynomial equations. And there may be non-solutions, but somehow you go to complex numbers, define some algebraic varieties. But that thing is geometry, topology, all these kind of 2 different studies. We need to define, less equal some kind of invariant, which is much easier to remember. So I'm not going to go to that, but in topology, you can define the homology groups. So any topological space can be associated some abelian groups, right? Small abelian group, which is much more accessible than the topological space itself. And also algebraic varieties, you can also define, Grothendieck define this homology group. So it's now not as refined as homology in topology, but it's now a vector space over some L numbers, when L is some primes. There's some kind of strange caveat there, that you choose some prime L, which is not, the characteristic of the fin K that you start with. So that is homology. And what is really important thing is now, if your algebraic varieties is defined over something K, then the Galois group now act on this vector space. So this is one of the part I want to stress on. In the case of just one equations, one polynomial, one variables, you have some 0-dimensional varieties. Then you have some Galois group act on finite set, right? And here you have many. Here you have many variables, many equations. Right? Of course, you should have the action of Galois group and set a point over C, for example, but it's kind of useless because it's just too big an object. But what you can remember are those Galois étant homology, some kind of use a finite dimensional vector space with an action of the Galois groups. So that is what we have to study for higher algebraic, higher dimensional varieties, more complicated system of equations. All right, so that is now the big questions in number theories. How to characterize the Galois representation that can occur in cohomology algebraic varieties. Right? That is, we don't want, we study algebraic varieties through those Galois representations, but we must know the properties of the Galois representation. There cannot be any Galois representation. Right? And another question is how to derive Diophantine properties from the Galois representation. So definitely it's more elementary if there are solutions. Right? So in the case of zero dimension, it's very easy to have action of Galois group on the finite set if there is a fixed point, and that would be the solutions. But now you kind of losing your hand on the point because the point of algebraic closed field, just too many of them. You don't know how to look at that. But you have finite dimensional vector space, reduction of Galois groups. So how can you, from that kind of linear algebraic object, can it tell you if there is a solution or not? So we don't know yet. That is in big, I think, something to do for the next 50 or 100 years. But we have know something. So got a big progress in mathematics in last 20 years or so. For the elliptic curve, this kind of torus, right? Then you know a lot, right? For elliptic curve, for this, when you have Galois representation, that is the Galois group acting on some finite dimensional vector space, then strangely that look like algebraic object need to be studied some kind of analytic thing, so called L function. I'm not sure what L function is, but you can produce some analytic function out of the representation. And the answer to characterizing it basically says that L function need to be a very specific kind of analytic functions, right? It looks very much like a Riemann zeta function. It has some kind of symmetries, has some kind of well-located zero, and so on. So in this case, this is what Weiss and Taylor's prove that, and his school, their school proved that is on those L function associated elliptic curve are it's called L function modular forms. And because of that, because L function modular form, they have all these kind of expected properties. And of course, if you want to generalize into higher dimensions, and that is called the Langlands program. So I am not going to venture into that. And the second question, I don't know, it's more difficult or easier or more difficult, but it's kind of different flavor. So now, given this Galois representation, or they're given this L function, how you can say about the, how you can tell about there is a K point, a solution or not. So that is in the elliptic curve, there is very beautiful conjecture due to Burton-Schunetten dyers, which is surprisingly discovered by computers. Right? At first, there's no theoretical evidence about that. They just look at the tables. And so they very surprising answer. The L function at some point, after analytic continuation, at some point they may have some points. And the orders of points tell you something about the solution to the cubic equations, elliptic curve equations. And of course, there's many conjectures for higher dimension varieties, Bellician conjecture, and so on. But I'm not going to go to that. But so that is my story. I think I finished before time. It's my story about Galois group, starting from from Babylonian plate to go to nowadays mathematics. Thank you.
Thank you very much. Are there any questions? Come.
So, sorry, I have some technical question and maybe a good chance to ask. So there is this old story about the non-existence of formula for the 5-degree equation. And then there was, I guess, one of the motivation for the 13th Hilbert problem was that this formula shows the roots as a function of coefficients, and it cannot be represented by a simpler formula which contains functions of less variables. Like in Cardano formula, we have function of 2 variables, addition and roots, and then we get this complicated dependence on 3 coefficients, two coefficients. And what is happening, is it something known now about this general question? If we have a equation of degree 5, and we consider the roots as a coefficients of, as a function of coefficients, can this function be represented as a composition of algebraic functions of fewer variables? Because the solution of Heidelberg problem says that if you have a continuous function, it's trivial somehow. But if in the original statement, is there a formula which will involve some kind of new kind of algebraic function of two variables and which will give the solutions? Is something known in this direction?
Yeah, I know the question, but unfortunately I don't know the answer. I think there's some recent research on that, but I cannot tell precisely. I'm sorry.
More questions? All right, if there are no more questions, thank you very much again.